Hello everyone, today we're going to be talking about the fundamental theorem of algebra. So what is the fundamental theorem of algebra? Well, every polynomial equation has to be an equation with a 0 on the other side of the equal sign, with a degree greater than 0, has at least one root, which are your x-intercepts, that's going to be in this set of complex numbers. The complex numbers where your leading coefficients could actually be 0 as well. Meaning that they could be real numbers as well as imaginary. A polynomial function must have at least one real root or two complex roots. So we would write them in the form a plus bi. So for our first example here, I'm going to show you what I mean by this. So x squared plus 6x plus 9 equals 0. So what we're going to do when we go to factor out, or we want to factor these to see if we can get our actual roots. So I don't have a GCF, so I'm going to go ahead and I have three terms, so I'm going to use the AC method here. I have 1 times 9 that's going to go on top and a 6 here, so I know 3 times 3 will get me my 9, and 3 plus 3 will get me my 6. So I'm going to go ahead and show that we have my new 4-termed polynomial. When I have 4 terms, I'm going to take the GCF of my first 2 terms, which is x. My remainder is x plus 3. And GCF of my last 2 terms, I have a positive 3, don't forget that plus sign, and x plus 3 here. Is still equal to 0. And then now my GCF that I have in both equal to those terms, and I also know I did my factor by grouping correctly, is x plus 3. My remainders I have left over are x plus 3 equals 0. Okay, I'm still not done actually solving for our 0, so what I'm going to do is I'm going to set each of these equal to 0, but see how they're actually the same? Some of you might see this written as like this, because it's this written twice. So that's how we could see x plus 3 squared. But I'm not going to do that just yet. But the thing is that I have to, when I set them equal to 0, I see that if I subtract 3, it's going to be the same for this one as well. So I actually only need to show one setting equal to 0. So I have x equaling negative 3. So this is my one real root. So that's the real value of it. I have a negative 3. I have no imaginary numbers or anything. But what we actually call this is a double root. And the reason why this is a double root is because we had the same value twice. I would have gotten this to be x minus x equals a negative 3 as well. So we see that it shows up twice. So it is a double root, but we only have one real factor. So this is a double root since negative 3, or let's actually write the actual factor. So since x plus 3 is twice, this is kind of going to be some kind of weird language, is twice a factor of our actual polynomial, the x squared plus 6x plus 9. So again, because we saw it happen twice, we had that x plus 3 squared. So this was our double root. And it occurred, our double root actually occurred at negative 3. Okay, so let me show you, and again we saw that with our little 2 right here. We had a degree higher than 2, so we were looking for 2 roots. We found one real root, but it happened to be a double root. That's why we ended up having 2 of them. Okay, for example number 2, I have x to the 3rd power plus 25x equals 0. Okay, every time I go to factor to identify my zeros, I always look for a GCF. I see I have a GCF first, so I have an x squared plus 25 equals 0. And then I see that I actually can't do an x squared plus 25. I don't have a negative sign in between there, so it's not a difference of squares. So I'm going to go ahead and set each of these equal to 0 and solve for x. This one's already solved for x, so this one is actually one of our real roots. And then here I need to actually do a little bit of work to actually solve for x. So I have x squared equals a negative 25. Once I take the square root of both sides, I added that in there, so I have now a plus or a minus sign. And then this negative right here is going to bring out my I. And then I also have the square root of 25, which is 5. So if we write that correctly, I have a plus and a minus 5i. So then these are my two imaginary or complex roots. So what I was actually looking for, if you look at your degree here, we had to have 3 of x-intercepts. So we happen to have 1 real with 2 imaginary. You're always going to have 2 imaginary when it's odd. So just to give you guys a heads up, because you end up getting your plus minus sign there. Typically, you'll usually have that. Okay, so that's our example here. And you guys, these are also called like this one is called a multiplicity of 2. It occurred twice, so multiplicity of 2. So you'll see that on the guided notes. Okay, the corollary of the fundamental theorem of algebra. So this is just the opposite. So now if we have a polynomial equation of the degree n, it's going to have exactly n roots. So that's what I've been saying with it's like our degree 3, it's going to have 3 roots. In the set of complex numbers, we happen to have 2 complex numbers and 1 real. And the complex numbers, they can actually be real coefficients as well, including our repeated roots, which was that x plus 3 squared. Okay. And then now what I want you guys to do, I want you guys to determine the number of roots each polynomial has, just by using each of our corollaries and our actual fundamental theorem of algebra. And these are the examples I want you to use it for. So x to the third plus 2x squared plus 6 equals 0. And again, you're just telling me the number of roots it should have. The other one I want you to tell me is 4x to the fourth minus 3x squared, cubed, minus 3x cubed plus 5x minus 6 equals 0. And then our last one is negative 2x to the 5th power, and then minus 3x squared plus 8 equals 0. Okay, so go ahead and determine the number of roots for each of those polynomials that we should have. You're not actually calculating the actual roots, I just want to know the number of them. Alright, you guys, I will see you in class. Have a good rest of your day.